Hello everyone. In this video we are going to talk about two important solvers in MATLAB. One of them is the solver called bvp4c, which is for boundary value problems or BVPs, and the other one is ode45 that I mentioned in some of other videos of mine, which is for initial value problems or IVPs. So a boundary value problem is a problem that you specify the conditions needed for your differential equation at different locations, and your independent variable is typically not time, it's location. So let's say you have a beam here, a simply supported beam. One side on the left is pivoted, the other side is on a roller, and you apply a uniform downward load of density omega or W here. The length of the beam is L, the Young modulus is E, and the section moment of inertia or area moment of inertia I for the beam are the important parameters. And Y is the downward deflection of the beam, X is the longitudinal coordinates. So y at x of 0 is 0, y at x of L is also equal to 0 because the two ends at the roller and the pivot does not deflect, they don't go up and down. The governing differential equation for the deflection is EI y double prime is equal to WLX over 2 minus WX squared over 2. And you can easily integrate y twice versus x and divide it by EI to get the accurate solution, which you can see here. Now, not always it is as simple as just double integration. It could be a differential equation that could be linear, nonlinear, or any form. And again, here you see that the independent variable is x, it's not time, and the conditions, the two conditions you need for the second order ODE are the deflection at two different locations. So that's a boundary value problem that you can see, and you can see it in lots of other different types of problems that you see in heat transfer, in flow of the fluid, and so many other things in engineering. The other type of problem we have is called initial value problem or IVP, where the independent variable is time, and the ODE, the differential equation, is described in terms of derivatives with respect to time. Here we show them with dots. So for this mass spring damper system with no external force, the governing equation, as you can see, is mx double dot plus bx dot plus kx equals 0. And you have two initial conditions. X of 0 is x naught, and x dot at 0 is v naught. The solution is going to be a what we call a damped vibration if this parameter zeta, which we call the damping coefficient, is less than 1 in magnitude. And this omega n is called natural frequency, omega d is called damped natural frequency. So these are two different types of problems that we'll see a lot in engineering applications, right? This one you see most of the time in problems that do not depend on time. They are like steady state solutions or something. This one are the problems that you see they depend on time, and in many applications you have the combination of all of those. So here we're going to look at these two different problems and see how we can solve them. So the major thing is both of the solvers we have, as I said, the solver for this type of problem is what we call bvp4c. There is another one called bvp5c, and they both work based on the same algorithm but different orders. And this bottom one is typically a little bit more accurate. It uses a fourth order method. This top one uses a third order method. But they are quite similar in terms of the final answer. If you want some more accurate thing, you probably want to use the bottom one. Ends up with smaller residual terms. And in this one, as I said, we are going to use ode45 most of the time, unless the differential equation is what we call a stiff. Then we use some other ODEs, like ode15 and so on. So both of these solvers, as I said, I'm going to use bvp4c. both of these, they can only solve first order differential equations. They cannot solve higher order differential equations. They can solve several first order ODEs at the same time, both of them, but nothing that you pass to them can be more than first order. So if you get something like this, second order, or this one, second order, you have to break it down to a bunch of first order equations, and that can be done using what we call dummy variables. So what you do here is you introduce this dummy variable, and how many dummy variables do you need? As many as the order of the ODE. So if it's second order, you need 2 dummy variables. And these dummy variables, typically you choose the first one. If you call it Z1, you choose it to be the function of interest, which in this case is y. Remember here the goal is to find y of x, right? And the other one you choose as the first derivative. So z number 2, you choose it to be y prime. That's one of the so many different ways you can choose the dummy variables. Pay attention that the selection for dummy variables is not unique. You can come up with so many different ways to select them, and that changes the shape of your differential equations, the first order ones that you will get, but it does not change necessarily or at all the actual solution to that variable of interest, to the dependent function. So if I choose this, then I will take a first derivative from both sides of these two equations. That makes it to be z1 prime equals y prime, but y prime was z2, so I can say z1 prime is going to be equal to z2, right? Because y prime is z2. And that makes the other one z2 prime to be y double prime, and for y double prime you get it from the differential equation. So y double prime here is, you plug it up here, and y double prime, or z2 prime, is equal to w over 2 times lx minus x squared. Right? And now if you look, clearly I have what? I have two differential equations, differential equation 1 and differential equation 2. They are coupled because you see z1 and z2 in the first one at least at the same time, but they are both first order, right? And as I said, this method can solve several first orders, and even if they are coupled, you need to solve them at the same time. So here you have two coupled first order ODEs. So using these two dummy variables, you change your one second order ODE into two first order ODEs that are coupled. And this solver has no problem solving such thing as long as they are first order. You do the exact same thing here. You choose your two dummy variables again, z1 to be your function of interest, x, which is what you need to find, and the second one, you choose it to be the first time derivative, x dot. And then you take time derivative from both sides of this, and that makes z1 dot to be x dot, but x dot is z2, and z2 dot to be x double dot, and x double dot, you find it from this equation. So from here, your z1 dot is going to be z2, because z2 is x dot, and z2 dot is going to be what? From here, clearly your x double dot, which is z2 dot, is negative bx dot, negative kx divided by m. Right? So this thing here is negative b over m x dot, negative k over mx. correct? That's what you have here. And so it's going to be negative b over m, but x dot itself is z2, and negative k over mx, and x is z1. So now, if you look, you clearly again have what? Two coupled first order ODEs. You see, they are both first order. And again, guess what? ode45 has no problem solving that, but it cannot solve a second order, right? So again, here we have what? We have two dummy variables. And we converted this 1 second order ODE into two first one that are coupled. So this is the first thing you have to do, right? You get a bunch of first order ODEs. And that's what you see here I'm doing in MATLAB. Like when I try to solve this boundary value problem, I need first the function. This is a user-defined function that defines those two what? Two first-order coupled ODEs. So you see here I'm saying y prime is equal to the function, whatever the name of it you want to choose, of x and y. The output of the function has two elements. The first one is y2, the second one is this relation. So let me explain this here as well. What is it? What's the difference between here and this notation I have? So what I do over there, I put this z1 and z2 into a vector, right? So I call it like z dot. So when in that algorithm or in that code, you see y prime, or here you see z dot, that's the same thing. So here for this one, when I say y prime, or you can call it z prime, whatever you want, I can say z prime. This is like a vector that is like z1 prime and what? z2 prime. And if you look at them, they are functions of the other z's, the right-hand side of them, or they are functions of x. So I can say this is a function of what in general? This is a function of what? X and the other z's, or z1 and z2, which collectively you can call these two guys what? Vector z. So z prime is a function of x and z. Here instead I call it y prime, but that's the very same thing. It's just a notation. You don't like it, you just call it what? You just call it z prime like this, and wherever you have y, you can call it what? Z. Correct? So you see here I have changed the notation. It's no big deal. And then I have these four global variables, E, L, I, and W, which are specified in my script. So this function clearly says the first prime, which is z1 prime, is z2, and that's exactly this equation. And then z2 prime is w over 2lx minus x squared. And of course, you have to also divide by EI. So there is one more thing we have to add here, and that is divided by 2EI, right? Because if you see, EI times y double prime is w over 2lx minus x squared. So we need EI as well added. That's exactly what I have done here in line 7. Or in my ODE, you see the same thing. I define z dot. In general, they are a function of t and z. In this case, there is no t, right? If you can see, all I have is, if I combine z1 dot and z2 dot into a vector z dot, then on the right hand side you see they are only a function of the other z's. But if there is a forcing function here, let's say if I had some f times sine omega t here, an external force, then here that force will be added instead of 0, and that will be added here. So on the right hand side, not only I have z1 and z2, I also have t. So I have to say in general it's a function of z and t, a function of the dependent variables. The first derivatives are the function of the dependent variables as well as the independent variable, and that's what you see here. The function of what? The dependent variables and the independent variables. So that's what you see. Not always we have the independent variable directly in my equations, but sometimes I do. And you see here again, z1 dot is z2, z2 dot is negative k over mz1, which is x, and negative b over mz2, which is ax dot. And there is no time of function directly. So this variable is really, as you can see, it says it's not used. Okay, so the first step for either solver is to define a function. That's what it does. It basically takes the dependent variables and the independent variable, and it spits out what? The first time derivatives. So that's what you're doing. This is either that my, here you called it my bvp fun, correct? So this my bvp fun, this one took vector z and x in general, and it spits out what? The z prime vector. And for this case, this my ode fun took from you, again, vector z, which includes x and x dot, as well as time. In this case, you don't have, and it spits out the vector z dot. So that's the first step, is to define the differential equations in a separate M file, which you can see here and here. Now, for ode45, the initial value solver, that's all you need, just the function. Once you have the function, then once you have defined the parameters, the other things you need is the time span, over what time range you want the problem to be solved, and then the two initial conditions, right? x0 and x dot of 0, these two guys here. Once you have those, which I have defined here, then you call that ode45 solver. You say what kind of function has defined my differential equations? The function my ode fun, so you use that and use @ sign to refer to the handle of that function. You pass to it the time span and the initial condition as a 2×1 vector. And this is a 2×1, and that's the exact same thing that you define here, a 2×1. And that's all you need. So here I called the ode45, and that gives me what? The answer, t and x. T here is a vector that has all the time points that the ODE solver used to solve the differential equation. The time points that are between 0 to 10 in the time span. And this capital X here is a matrix with two large columns. The first column are all of the values of your first dummy variable, z1 or x, the position, and the second one is all of the values of z2 or x dot or velocity that you have. So if you want to plot the position versus time, you plot t versus the first column in x, and that's the position. If you plot versus second column of x, that's velocity versus time. So here you see, once I obtain the solution, I will plot the numerical solution, and then on the top of that, I plot the exact solution, and the exact solution here is, as I said, the damped oscillation. So I calculate all of these three parameters, omega n, omega d, zeta, and then find the exact solution, like you can see here. define it over there, call it x exact, and then plot that one on the top of the original one. So, and you can see that they are almost identical, right? Here, the markers circle are the numericals and the triangles are the analytic solution. And anywhere that you zoom, you can see that they are almost perfectly coincident, right? So your ode45 in this case is doing a very, very good job of solving for this initial value problem. Okay, now for the boundary value problem, not only you need the function here that specifies the first order coupled ODEs, you need a second function that provides the boundary values. And for this case, the boundary values I have are both 0. So at the left side of the boundary, which in MATLAB you call it A, and on the right side, which you call it B, in both cases, y at A is 0 and y at B is equal to 0. So what you need to provide in that boundary value functions is the functions that are equal to 0, these two functions, what they are. So since 0, as I said, x of 0 is equivalent to a, so one of them is going to be y of a, which is 0. The other one is going to be what? Y of b, which is 0. So one of them is y of a, the other one is y of b, and that's what you exactly see here. Y of a and y of b, 1. Now, what does this 1 here mean? Basically, it means the first variable of your dummy variables, right? Because remember, you have two dummy variables, y and y prime. And what you are saying is, hey, only what? The first dummy variable, variable 1, has a value of what? 0 on the left and a value of 0 on the right, correct? For example, if instead you wanted to say, hey, y prime here at the left is 0, of course, for a pivot, it's not going to be 0, but let's say if you had a cantilevered beam like this, and you had this constant load of W all over the place, correct? Then at x of here, at x of 0, you had y to be 0, right? And you also had y prime, or the slope, at 0 to be 0. If that's the case, then how would you show it in MATLAB? Well, this is y of a, but number 1, and this is y prime of a. So you have to change this to what? Instead of y of a at 1 and y of b, because b means the right-hand side. Then you say what? Y of a at 1 is 0, and y of a 2. 2 means the second dummy variable, right? So here you have to say y of a, the left-hand side, number 1, the first variable, which is y, is 0, and then y again at a, the left-hand side, but the prime of it, which is variable number 2, is 0. So this is how you provide that, right? These guys. These are equal to 0, and that will change how you define the boundary condition, right? Or if one of these were not 0, let's say, for example, at y of 0 here, it was like 0.5, right? Let's say at y of 0, the y was not 0, was 0.5. Then you bring that 0.5 to the left side and set it equal to 0, like this. Then this thing here is going to be the function that is equal to 0. So your left-hand side equation will be y of a. It is going to be what? Is going to be y of a number 1 minus 0.5. That is equal to 0. So here you subtracted a 0.5. Right? That is equal to 0. So hopefully this is clear what it is doing. A means the left-hand side, B means the right-hand side, Y means the first dummy variable, and 2 means the second dummy variable that you chose, in this case, Y prime. So this is how you define the boundary conditions. And now that you have boundary conditions and the function, you go here and you define your parameters. Here I choose 2 different meshes. Here, this method is a finite difference method. So in ode45, the time points that you have, the algorithm would select by itself. So ode45, when you plot x versus t, it selects, you give it the initial time and the final time, but the time points in between these, correct? Let's say you start here and then go up and down and up and down, and you do some oscillations like this. The values of these time points, it's the algorithm, the ode45 algorithm, that decides where to put these time points. Okay? And typically they are not equally distanced. They are not what we call fixed step size. These step sizes are different, so we call them variable step size. Okay? Because if the right-hand side function, this guy, is fast changing, it tries to use smaller step size. If it's slow changing, it uses bigger step sizes to accelerate your solution. So the points in between you do not need to provide for initial value problem, but for the boundary value problem you do. You have the x of 0 and x of L, but in between those you fix a specific number of points, or maybe here on this one, you fix a specific number of points, and these points you call them node, right? So you break your domain into what? Into a bunch of nodes. You can have these nodes to be all the same size, or you can choose them to be what? Different sizes, okay? So by no means you have to have all of these guys to be the same, right? So each node could be a different length from one of the previous nodes, or you can make the, not nodes, the elements. Each one of these elements could be a different size from the rest of them, or they can be all the same size. Okay, so these guys are elements, and the intersection points of them are what we call nodes. And then the boundary value problem tries to make minimal, what we call residual at these nodes. And residual means, remember here, if you go to your forcing functions, these guys, right? These are the forcing functions that you have, and also you have some boundary conditions. So the boundary conditions are only enforced at the 2 ends, but in between you also try to minimize the error for the what we call the discretized version of these equations, because it doesn't solve these equations directly, it discretizes them into what we call difference equations, finite difference equations, finite difference. And in those equations, it tries to minimize the amount of error, which is the difference between the left and the right side. And so the more points, the more nodes, the more elements you use, at more points, it tries to minimize the amount of error between the left and the right side of these governing equations. And that means it does a better job of approximating your exact solution. So if you want to get a better solution, you need to add more nodes and more elements. So it does minimizing this difference between the left and the right hand side, which we call residual, at a lot more points and get you a better solution. And that's what you see here. In this script, I'm using 2 different types of meshes. In one of them, I bring the whole range into 5 elements. In the other one, I make it 10 elements. And then when I call my boundary value 4 or 5c, right? They are the same solver, as I said. This one is a little bit more accurate. They are using the same method except for the order of it. What you need to pass to this solver is what? The functions that are governing your differential equations, which we already defined. You also need to pass, again with another @ sign, the functions that describe your boundary conditions, which we already have defined. And you need some initialization. Okay, and initialization means how much is the value at these nodes in the beginning, because this method starts with some initial guess of how much, let's say in this case, is the deflection of each one of these nodes, and then tries to what? Tries to, based on the left and right hand side of these equations, tries to minimize the error between left and right. Because if at a node, let's say instead of the actual deflection, I say, well, I guess it's just this amount of deflection here at this specific node, instead of this one, which is the actual solution, maybe it's this one, I just guess. If I plug that value of deflection and the resulting number that comes from that, including the y prime, which can be approximated by y of next point minus y of previous point divided by 2 delta x, if I do that, then the left and the right hand side of these equations will not be the same. So I get big errors. So I have to keep modifying those initial guesses until what? Until I converge to some numbers. For those numbers, the left and the right hand side of these governing equations are minimally different. The difference between them is less than some very small threshold. Then I say, well, my guess has converged to actual solution. So you definitely need to start from some initial guess of your answer for these nodes. And I know some of you might say, well, what do you mean by the difference between left and the right side? What do you mean by the residual? What do you mean by error? Well, let me clarify that with you, because might not be very well clear. So here, look at this governing equation. You can either use that governing equation or you can use these 2 sides. Doesn't matter, that's the same thing. So if I look at this original one, this is the equation I have. Right? And let's say this is my beam that I broke into 5 elements. So this is x of 0, this is x of L. And let's say I have a node here at x equal 0.4 L. At this point, I guess the amount of deflection is this much. Whatever, let's say y guess. So I think that node will come down to here. This node, it comes down to maybe here. This node doesn't move, this node doesn't move. These 2 nodes, maybe they move this much. Correct? So how do I know that guess, this y of g that I guess, that's a correct answer? Well, I tried to use this shape of the beam that I just got, which is this guy. I tried to use this beam and see whether this shape of the beam matches this equation or not. And you might say, well, how? To do that, as I said, I need to discretize my derivatives. So y prime at any point is going to be approximated by y at the next node, so y prime at any x, if I want to use the central formula for central finite, so this is what we call the finite difference method, which we use for discretization. I have a video on this topic. If you want, go ahead and look at my playlist called Partial Differential Equations. You see the solution of those using finite difference method. So you see more detail about this. But if I approximate it by y at the next node, so if this is xi, at xi plus 1 minus y at xi minus 1, and then divided by xi plus 1 minus xi minus 1. And then I can approximate y double prime at any node by what? It's going to be y at xi plus 1 plus y at xi minus 1 minus 2 times y at xi divided by what? Divided by the distance. If they're all equidistant, it's going to be delta x squared. So delta x, if I call this whole thing delta x and I assume it's constant. Right? So in this equation, I'm going to approximate my y double prime by that. So if this is yg, let's say 1, this is yg2, and this guy is yg3, and maybe this one is yg4. Then if I want to check at this node whether my equation is correct or not, what do? I say E times I times y double prime at that node, which is, based on this definition, it's y at the next node, so xi is here. This is xi plus 1. This is xi minus 1. It's going to be the y at the previous and the next node, so it's going to be yg number 3 plus yg number 1 minus 2 times yg number 2 divided by delta x, which is this much, and this delta x is clearly, in this case, 0.2 L. Squared. This should be equal to what? W, which is the same at any node. W is the same here. It doesn't matter. W is not a function of x. If it was, I had to find it how much it is at that specific node. In this case, it's not. So it's the same W over 2 L times x, and x here is xi minus xi squared. And what is this xi for me? It is 0.4 L, as I just said here. Right? So I look whether the left and the right side are equal or not. And the difference between them, if I subtract them from each other, this is what we call a residual or error. At which node? At node xi. And I can calculate a residual term for any other node. And then what? My goal is to update these YGs such that at the end of the day, these residual terms become what? Becomes as small as possible. So that's how these methods work. They convert your continuous equations into discrete equations like this using finite difference method. They calculate residuals, they start from some initial guess, and then their recursive algorithm tells you how to update these so that these residual terms becomes as small as possible. Good. So you see why you need an initialization. Now here, I have two different types of initialization that I pass to my solvers. One of them, as I said, using 5 elements. One of them is using 10 elements. And for one of them, I said, I guess it's a constant number for Z1 and Z2, which is Y and Y prime all over the place. So I said, hey, I think y for all of these nodes, y for all of these nodes is 1. So if this is the original beam, everything goes down by 1 unit. So yg for all of these guys is equal to 1. Not only that, y prime of g is also equal to 1. If that's the case, then this is not going to be the shape because you also have a slope here. So your equation is going to be basically a slope plus 1, so your beam has to end up like this. It has a slope of 1, and then everything goes down by 1. Right? So your y of x is basically, the solution is something like x plus 1 or something like that, correct? The value everywhere is 1 except for the slope of 1 or something like that, which is definitely not true because I know the two endpoints do not move. Right here at x of 0 you have 1 displacement, and at x of L, which is 3 here, you're going to have 4 units of displacement. So definitely that's wrong. That's a wrong guess. But even this method with the wrong guess, you'll see for both y and y prime still works and still able to update the yg's and converge to the actual solution. What you can do better is say, well, I tried to give it a guess, and this guess is at least satisfies the boundary condition. So instead of me just throwing some random function like constant or constant slope, I tried to pass maybe a parabola to it like this. So at x of 0, it's 0. And at x of L, it is also what? 0. And then in the middle, maybe it becomes maximum or minimum. And that's what I see you see I have done here. I defined a function called guess. This function is defined down below here. And it is a quadratic function, as you can see. This is x times L minus x. Clearly at x of 0, it's 0. At x of L, it's 0. In the middle, it is going to be minimum. And by the way, this L has to be the same global L. So here I have to just say global L, and I don't need to define it again. And this is the y prime. Remember, the first guess you pass to it is y, and the second guess is y prime. So this is exactly the x derivative of this function. xl minus x squared, the derivative of that is L minus 2x. Good? And when I want to pass the values of those yg's, how do I do it? I say, hey, get the values of the mesh, get the x values of the mesh, which are the node positions basically, pass to them to this function guess, and whatever y that gives you, those yg's, use them as your initial solvers, initial value for the solvers, the initial deflections at the nodes. So you see here, one time I used a function that depends on x, one time for both y and y prime. One time I just said I don't know and just passed it some constant numbers. None of them might be the actual solution. It doesn't matter. It just needs something to start with. And in both cases, you'll see when I run this, it is going to do a relatively good job. So first of all, you see here, I use different solvers, different meshes, different initial conditions, the same boundary conditions for both, the same functions actually. The only thing I pass to them is different meshes, different initial conditions. And I got something called a solution out of these solvers. Now this solution is a structure. This structure, if you look at it, if you look at solution, right? If you look at solution 1, it is a structure. It has some x values. These are your nodes. It has some y values, which are the solutions. It has some y prime values. And it has some stats. Okay, so it's a structure. So if you want to plot x versus y, then you have to do what? You say plot x versus y. And this y here is the first column of that is y, the second column of that is really the second dummy variable. So I just apply first column of y versus x. And then I do the same thing for second solution. I also have the exact solution, which in this case is a very simple solution, right? Just integrating both sides twice and dividing by EI, so it's a fourth order polynomial. And you see I have defined that as well here, call it y exact. And then I plot the different solutions with different number of mesh elements and solvers versus analytical solution, and this is what you get. The black one with triangles is analytic, the blue one with circles is the quadratic guess with 10 elements, and the bvp4c, right? As you clearly see, I passed here solution 1, actually it's bvp4c. So I passed the better mesh to the weaker solver, and I passed the bad mesh to the better solver. So this is 5, this is 4. Right? And you clearly can see that when I use enough of elements here, 10 elements, or not enough, I mean more elements, the solution is way closer to analytic than when I use what? 5 elements. Okay, although here with 5 elements I use the better solver, a more accurate solver, but definitely more elements is having a larger effect on the total error than the higher order solver. Okay, so if somebody tells you what is it that you want to change, is it the guess that is the most important factor? Is it the number of elements, or is it the solver that makes your solution the most accurate? The answer is what? The number of elements. That's the number one factor. Try to use not larger number of elements. That makes your solution a lot closer to analytic. If they are the same thing, then the next factor is going to be the solver. The solver, this one has a better convergence than this one in most of the times. And of course what? Then it comes down to which one of the guesses was initially closer. Now, the closeness of the guess to the actual solution does not change the final answer. They will go as much as the error in those residuals is above a threshold. It just makes it take more time. So if you start with a better guess, you converge to the final solution faster. If you start with some guess that is completely off, like those constant numbers, it takes more time for the solver to converge. But at the end of the day, both of them will converge to the same solution. So the initial guess does not change the accuracy really of the final solution. It changes the computation time. For the accuracy, you need more elements. And if the elements are the same, then bvp4c typically has a tighter tolerance and threshold than number 4. And you can see those under the stats for each one of these guys. Okay? If you go here and look under these stats, right? So remember when I use solution, it has a stat. And now if I say solution1.stats, it shows you the maximum residual term that you have, and how many times something was called, some solver was called, how many points were used, and so on. Okay? So my final advice, use more elements. Try to give it a guess that at least satisfies the boundary condition. The rest of it is not as important. And then, if possible, use bvp4c, if not bvp4c, okay? But both of them do a decent job, because this problem was, of course, a very simple problem. Once the problem becomes more complicated, then it is not going to be as easy, right? So they take more time. They might have some error and so on, and there might be no analytic solution like this to compare against. So hopefully this video was useful to you and you learned how to solve both boundary and initial value problems in MATLAB using bvp4c5c and ode45. Thank you for your attention. I will see you in my next video. Thanks.